Today we're going to learn about the rules for finding the derivatives of inverse trig functions. You can create these using either some ideas that you know about trigonometry, or I'm going to show you another way. You can also use the inverse rule for derivative functions. I'm going to show you that as well. In the end, I don't recommend trying to, I'll just generate these rules on the test. I recommend memorizing them. Okay, it takes too long. So, for example, if I'm trying to find the derivative of arc sine, so your book is one of those ones where when they say arc sine, the capital A means that it is the function arc sine, not the inverse sine where it goes on forever and ever and ever, amen. Okay? It's a restricted domain on the original that gives a one-to-one correspondence between the two. So, if we let x be equal to sine of y, then taking the sine inverse of both sides, we would have the sine inverse of x is equal to y. So if I take this part and take the derivative of both sides with respect to x, on the left side I just get 1. On the right side, the derivative with respect to x of the sine of y will be the cosine of y, and then because of the chain rule, times dy dx. Solving that for dy dx, dividing both sides by the cosine of y, gives me that dy dx is equal to 1 over the cosine of y. Since cosine, if I take cosine squared plus sine squared, it's equal to 1. So since you don't need to write this, but cosine squared y plus sine squared y is 1. That means that cosine squared y is equal to 1 minus sine squared of y. So cosine of y is the square root of 1 minus sine squared of y. The reason that we did this is because now we can get it back into terms of x. So the derivative with respect to x of the sine inverse of x is 1 over the square root of 1 minus x squared, provided that the absolute value of x is less than 1. We have to do that because if it's not, then we get imaginary numbers in our denominator here. We would rather avoid that. You could also do this by the derivative rule for inverse functions. If you said, let f be sine of x and g be f inverse of x, and we're trying to find what g prime of x is, that'll be 1 over f prime of g of x. Right, that's the derivative rule for inverse functions. The derivative of f is sine, so this can be 1 over the sine of f inverse, so this will be 1 over the sine, back up just a step. The derivative of the sine is the cosine, so it's going to be the cosine of the sine inverse of x. And you could, at least in theory, leave it like this, but it's not particularly satisfying because it still has the sine inverse in it. What you have to do is go, okay, I'm going to make a reference triangle and go, okay, to find the sine inverse of x, that's an angle, theta, whose sine is equal to 1. So the opposite leg over the hypotenuse has to be equal to x. Then I want the cosine of that angle. by using the Pythagorean theorem and solving for this side, I get that the length of this side is 1 minus x squared, or the square root, excuse me, of 1 minus x squared. So this would be 1 over the square root of 1 minus x squared. So you can do it that way also. Either way, trying to do this from scratch, you either have to use a trig identity or you've got to use a reference triangle. And both of those, it's kind of a, you have to have what I call mathematical inspiration, where you're like, what am I supposed to do with this? Oh, I know what I can do with this. So it's not super straightforward. Again, I suggest you just straight up memorize this. Okay, I'm not going to take you all the way through each of the other ones, but it's the same idea. We set tangent of y equal to x so that y is tangent inverse. We take the derivatives, solve for dy dx, use a trig identity, and we get this. Notice that the tangent inverse doesn't have a square root on it, and that it's 1 plus x squared. And then the derivative of arcsecant, it's a little uglier because there's a plus minus involved here when we take the square root. And the way that that's dealt with is we just make it the absolute value. Then we don't have to worry about the plus minus. So the derivative with respect to x of the secant inverse of x is 1 over the absolute value of x times the square root of x squared minus 1. The way, sometimes students are like, I have trouble remembering which one is which and what order this goes in. For me, I think about these x's are next to each other. That helps me remember, oh yeah. And secant is the more complicated one. All of the other ones, the derivative of arc cosine, arc cotangent, and arc cosecant, are exactly the same except they're just the opposite sign. So staying with our theme of when you have the derivative of a cofunction, it works with the arc cofunction also, that the derivatives are negative. All right, so let's do this. Let's find the derivative with respect to x of the sine inverse of x cubed. So although they didn't write it this way, this is a composite function. It's the sine inverse of x cubed. So that's going to be equal to 1 over the square root of 1 minus x cubed squared times, because of the chain rule, the derivative of x cubed, which is 3x squared. So this is going to be 3x squared over the square root of 1 minus x to the 6th. Part of why it's important to do enough of these is that later on we'll actually be going in reverse, where you'll be given something that looks kind of like this and say, well, what function could I have taken the derivative of to have ended up with this ugly thing? And you have to go, oh, well, that's sort of in the form of the arc sine, and if I rewrite that as x cubed squared, then this is the derivative of the inside part. So you're working backwards. It's called anti-differentiation. And actually, as a general rule, anti-differentiation is harder than differentiation because you're not given, there's a rule for everything like we have for derivatives. It's what derivative rule could I use in reverse? So it's a little more difficult. All right, so let's take a look at this. The particle moves along the x-axis so that its position at any time t greater than or equal to 0 is given by x of t is equal to tangent inverse of the square root of t. Find the velocity of the particle when t is 16. So we need to find the velocity function to start with. V of t. We'll start with the outside part. The derivative of tangent inverse of something is 1 over 1 plus whatever that something was, which is the square root of t, squared, times, because of the chain rule, 1/2 of t raised to the negative 1/2 power. If we simplify that, and you don't have to simplify it, you can just go ahead and crank the numbers if you want to, but this would be 1 over 2 square roots of t times 1 plus t. And this is part of why, as I told you earlier, why doing antiderivatives is more difficult. When you look at this, it doesn't look very much like the arctangent derivative, where it's just 1 over 1 plus something squared.
Student or staff member has not taken their pictures for the yearbook, you may go to room 404 for the next 5 minutes. You have 5 minutes to go to 404 to get
Run!
your picture made. If you have not done so, please head to room 404 at this time. Thank you.
But what you have to think about is that this would be 1 plus the square root of t squared. And then all this other stuff comes from the chain rule. You undo the chain rule also. Yeah, it's fun. All right, let's try this one. The derivative with respect to x of the secant inverse of 4x to the 5th. So we'll start with the secant inverse part. So that'll be 1 over the absolute value of whatever the something is. So that's 4x to the 5th. Times the square root of whatever that something is, 4x to the 5th squared minus 1, times, because of the chain rule, the derivative of 4x to the 5th, which is 20x to the 4th. Well, the 20x to the 4th is in the numerator, so I can divide the 4 into that, and that'll leave me a 5 in the numerator. In the denominator, I'm going to have the absolute value of x times the square root of, what'll that be, 16x to the 10th minus 1. All right. Any questions about that? All right. So let's find an equation for the graph of the line tangent to the graph of y equals cotangent inverse of x at x equals -1. Verify your answer graphically. Okay, so we'll start by finding the point. We know the x-coordinate of the point is -1, so we want y is going to be the cotangent inverse of -1. And this is almost immediately where the problems start for everyone. Not so much that they can't find a value, but the question becomes, and I have to look this up every year. I'll be totally and completely honest on this. When you're doing cotangent inverse I'm like, okay, when it's negative, which quadrant should I be looking at? Should I be looking in the second quadrant or in the fourth quadrant? Because that's where cotangent is negative. And so, because I do this every year, I'm going to find a place to look it up. I don't remember. I don't do cotangent inverse very often. Okay? So, let's see. Which one of my books has this in it? Where's a really, really old calculus book? Well, I must have taken that one home. The other place to look is to see, did I steal this problem right out of your book? Because I've been known to do that as well. Okay, so it is in the second quadrant. So that's going to be 3 pi over 4. So I know that my point has coordinates -1, 3 pi over 4. Then I'll find the derivative, y prime. So the derivative of cotangent inverse, it's a cofunction, so it's going to be -1 over, and it'll be still 1 plus x squared. So this means that the slope will be equal to -1 over 1 plus 1 squared is -1/2. So the tangent line will have an equation of y is equal to 3 pi over 4 minus 1/2 of x plus 1. Now, they ask us to verify this graphically, and that can be difficult depending on what calculator you're using. So on a TI, there is no cotangent inverse built in, at least not that I can remember. Check yours. They may have updated it since I last did my calculator. So I'm going to go to y equals, and I'm going to clear all this stuff out. I guess I'll look, well, it's not in the math menu. Let's look in the catalog. I'm pretty sure that mine does not have it. Nope. Doesn't even have cotangent. Does yours have it in there in the catalog?
Mine died.
Yours died?
No, I don't think so.
Okay.
I'm on the D.
So there is, and this is actually in your book, calculator conversion identities. And I'm like, okay. And you can tell I don't know these because I don't use them very often. But secant inverse of x is the cosine inverse of 1 over x. And before you think, oh, well, they'll all follow that pattern, so it'll be easy. No. The cotangent inverse of x is pi over 2 minus the tangent inverse of x. And then the cosecant inverse of x is, again, like the secant inverse one. It's the sine inverse of 1 over x. All right, so now I'm going to graph this thing. So I need pi over 2 minus tangent inverse of x. And then I'm also going to graph 3 pi over 4 minus 1/2 of x plus 1. Yeah, that looks pretty good. Might be better able to see it if we zoom in a little bit more. Maybe not. Yeah, you can kind of see that that's the tangent line over here. I'm curious. I haven't actually looked. I don't know if the NumWorks calculator has this on it or not. Doesn't list it. That doesn't mean that it's not there. I just don't know where it is, if it's anywhere. Anyway, you get the idea. You can tell that I'm not going to major on this, and this isn't something that they ask a lot on the AP exam for that kind of thing. They are interested that you know the derivatives of those, but that's about as far as it goes. All right. Okay. And that's it then.